we propose a new 3D shape generative method using denizen diffusion models. This figure is visualization of generated 3D shapes. We successfully applied denizen diffusion models to the 3D shape generation in the form of meshes. As shown in the figure, by iteratively reducing noise in 3D space, we can generate new 3D shapes. This figure is overview of our framework. The goal of our method is to generate 3D shape in the form of mesh while alleviating memory issues by separating the process into two stages. In the first stage, a diffusion-based model generates a low-resolution SDF of 3D shape. Using the low resolution as a condition, the second stage performs super resolution to generate high resolution SDF. After that, with simple conversion algorithm, the output SDF can be converted into mesh. This slide is previous methods for 3D shape generation using diffusion models. They utilizes diffusion framework for point cloud and demonstrated their impressive performance compared to the previous methods. However, the point cloud-based 3D shape generation has limitations. In this slide, we will discuss about limitation of point cloud for 3D shape generation. Point cloud is partial representation of 3D shape, so point cloud has limited applicability. In addition, as you can see in the red circles, the reconstructed meshes have an even and irregular surface. Therefore, we find another representation for 3D shape generation. In this slide, we will explain about why we choose voxel-shaped SDF instead of point cloud. Voxel-shaped SDF has several advantages over point cloud. As you can see in the figure, the SDF can be converted into mesh simply using Marching Cubes algorithm. And it can utilize power of convolutional neural network. In addition, in all of our experiments, we use TSDF instead of SDF by clipping SDF values to reduce unimportant information. And the right figure is the reconstructed mesh from the voxel-shaped TSDF. In this slide, we will discuss about challenges of processing high-resolution voxel. Due to cursive dimension, processing 3D data requires large memory and computation. For example, a 2D image feature with 32 channels need 2 megabytes, but 3D requires 256 megabytes. Because training neural network makes thousands features, this will exceed memory computation limitation. Therefore, processing this high-resolution data in 3D is a big challenging problem. This slide is overview of our framework. To overcome the problem of voxel, we propose a new two-stage generative process. The first stage is diffusion-based generation model, focusing on generating semantically import information of 3D shape as a low-resolution SDF voxel, which is coarse 3D shape. The second stage is diffusion-based super-resolution model, focusing on generating details of 3D shape of the low-resolution voxel to make fine detailed 3D shape. By splitting the generation process into two stages, we can achieve effective and efficient generation of high-quality 3D meshes. In this slide, we will explain about details of the first stage. Purpose of the first stage is to generate low-resolution SDF voxel using diffusion framework. During the training phase, the model learns how to was SDF voxel. During inference phase, by iteratively applying the denizen step from the Gaussian noise, we can generate a new low-resolution SDF. With this first stage diffusion framework, we can generate low-resolution SDF voxel, which is used in the second stage. In this slide, we will explain about details of the second stage. Purpose of the second stage is generating high-resolution SDF voxel through super resolution. During the training phase, the model learns how to was high-resolution SDF voxel with condition of low resolution. During inference phase, by iteratively applying the denizen step from the high-resolution Gaussian noise, we can generate a fine detailed 3D shape. With this second stage diffusion framework, we can generate high-resolution SDF voxel, which is fine detailed 3D shape. In this slide, we will explain our patch-based training scheme for high-resolution super resolution. Even with the two-stage approach, processing high-resolution voxel is still a difficult problem because of large memory and computation. To alleviate this, we use patch-based training approach. We sample small patches of the low and high-resolution voxels, and the second stage, model learns how to was local area of the 3D shape. We can apply this patch-by-patch scheme only for training phase, because the inference phase need no much memory than training phase. With this patch-based training scheme, our method can be applied much higher resolution. In this slide, we will discuss about applicability of our method. Our framework use UNet architecture of SR3 with a few modification, and our model can be extended to other conditional generative methods, such as shape completion. Specifically, for voxel-shaped condition, our method can be extended into conditional generation by simply concatenating it. For point cloud condition, we borrow encoder of convolutional occupancy network to make the point feature into voxel. Then, we give this conditional information through adaptive group normalization similar to class condition. Because of simple structure, our method can be seamlessly extended for various types of input, data, and tasks. This is objective functions of our frameworks. The first and second stage models are trained by comparing predicted shape and real shape. The difference between conventional diffusion is that our framework predicts the denoised shape instead of noise, because TSDF value is low frequency far from the surface, but the Gaussian noise has even frequency in any location of 3D space. Therefore, we deduce the reason is that predicting low frequency TSDF is easier. This is quantitative and qualitative evaluations of single category generation. We measure generation performance by comparing distributional similarity between generated and real data. As mentioned earlier, generating mesh is much difficult problem than point cloud. As you can see in the figure, even though output of our framework is mesh, outwork outperforms in most of metrics. This is visualizations of generated 3D shapes from our method. We arranged the generated 3D shapes in order of resolutions. Our method can generate various and plausible 3D shape in the form of meshes instead of point cloud. This figure is visualization's shape completion result. With given partial 3D shape in the form of SDF voxel, our proposed method predicts the complete shape. As you can see in the figure, our methods show various and plausible candidates with regard to a given same condition. This figure is visualization of shape completion results from point cloud of real-world dataset. We train our model to predict complete shape from partial point cloud of our dataset. Our model can generate various 3D shapes from even unseen dataset. In this work, we have proposed a novel diffusion-based 3D shape generation approach. Our two-stage method generates low-resolution 3D shape and then produces high-resolution with a condition of the low-resolution one. For memory efficiency, we learn the second stage model in patch-wise manner, which allows us to perform super-resolution efficiently in high resolution. In addition, our method can be seamlessly extended to multi-category 3D shape generation and shape completion. Experiments demonstrate that the proposed method can generate high-quality 3D shapes in the SDF domain with superior generative power. This is references of our presentation. Thank you for watching our presentation.